random variables x1, x2, all the way to xn are jointly Gaussian if any linear combination of those random variables yield a Gaussian random variable. So for every alpha 1, alpha 2, all the way to alpha n, and those guys are real numbers, if alpha 1 x1 plus alpha 2 x2 plus alpha n xn is Gaussian, and this is true for any selection of those alphas, then we say that this collection of random variables is jointly Gaussian. And if those random variables are the components of a vector, then we say that the vector is Gaussian. Now, if this quantity is Gaussian, then it is characterized by the mean or the first moment and the variance. So what is the mean and what is the variance? So apply expectation. Expectation is linear, so this is the summation j from 1 to n alpha j expected j. So this will be the first moment of this Gaussian random variable. If we collect the first moments in a column vector eta, so this is expectation of x1, and then here is eta2, which is expectation of x2, and so on. Then if we also collect the alphas in a column vector, alpha 1, alpha 2 to alpha n, then the mean value, which is this summation, can be written as alpha transpose eta or eta transpose alpha. For the variance, let's subtract from each xj its first moment, which is eta j. Now, the second moment of this quantity is the variance of this weighted sum of the x's. The square of the sum is a double sum okay, and then we will have xj minus eta j and xk minus eta k. By linearity of expectation, this is summation j from 1 to n, summation k from 1 to n, alpha j, alpha k. Applying the expectation to this yields the covariance of xj, xk, because the covariance is simply expectation value of the product, xj minus its first moment times xk minus its first moment. So we get a quadratic form, we get a double sum here, which can be written as alpha transpose. So alpha again is this vector, column vector with the alphas. And then we have alpha here, and in between we will have cxx, that's the covariance matrix of random vector x, which by definition is the expectation of x minus eta. So this is the vector of the first moments, x minus eta transpose. And element jk in this matrix is simply the covariance between random variable xj and random variable xk. So this summation here is Gaussian for any choice of the real numbers alpha 1, alpha 2, all the way to alpha n. The first moment is alpha transpose eta, where eta has components expected value of x1, then expected value of x2, and so on. And the variance is the quadratic form, which is alpha transpose cxx alpha. Cxx is the covariance matrix of random vector x. So it is the expectation of the outer product of x minus its mean vector with itself. So it is expectation of x minus eta transpose. Element kj in this matrix is the covariance between xk and xj, which is defined with this expectation. If we have jointly Gaussian random variables, then it must be the case that each one of them is a Gaussian random variable. Moreover, any subcollection, so if we choose, let's say from the x's, we choose x1, x4, and x7, those three guys, x1, x4, and x7, are also jointly Gaussian. Also, the sum of the random variables will be Gaussian. To prove these results, we just make a particular choice of the alphas. So, according to the definition of jointly Gaussian random variables, if x1, x2 to xn are jointly Gaussian, for any selection of those alphas, this random variable here, which is the weighted sum, is Gaussian. Then it is Gaussian for a particular choice. If we choose alpha 1 to be 1, alpha 2 to be 0, all the other alphas to be 0. This is a choice for alphas. Regardless, it must be the case that for this choice also, this random variable is Gaussian. And for this particular choice, what is the weighted sum? It is simply equal. It is simply x1. So for this particular choice of the alphas, the sum is Gaussian and the sum is x1. So x1 is Gaussian. The other results can be derived basically by the same idea. For example, we want to show that the sum is Gaussian. The sum is Gaussian. Well, the linear combination is always Gaussian. Okay, so this is Gaussian if we choose every alpha to be equal to 1. So it must be the case that the sum of jointly Gaussian random variables is itself Gaussian, and so on. Note the following, that the converse is not generally true, which means that suppose that I know that x1 is Gaussian. So as a random variable, it is Gaussian random variable. x2 is Gaussian. This does not imply that they are automatically jointly Gaussian. If each one of them is Gaussian, it has a Gaussian distribution, then they are not necessarily Gaussian. It may happen that there exists alpha 1 tilde and alpha 2 tilde. So it may happen that there exists these two real numbers such that alpha 1 bar x1 plus alpha 2 bar x2 is not Gaussian. So if we know that each one of them is Gaussian, to be jointly Gaussian, we need to verify the definition. We need to make sure that any linear combination of these guys, any alpha 1 x1 plus alpha 2 x2 is indeed Gaussian. We can come up with examples or counter examples, if you like, to show that I can find x1 that is Gaussian, x2 that is Gaussian, but for example, their sum is not Gaussian. And so in that case, they will not be jointly Gaussian. Okay, so this is very important. I cannot say that the sum of Gaussian random variables is Gaussian. What I can say is that the sum of jointly Gaussian random variables is Gaussian. I can say that in a collection of jointly Gaussian random variables, each random variable is Gaussian. But I cannot say that a collection of random variables in which each one of them is Gaussian is jointly Gaussian unless I verify that any weighted sum of them will yield a Gaussian random variable. To derive some important results regarding the jointly Gaussian random variables, we will make use of the characteristic function. So the characteristic function, if we have a random variable, so random variable z, then the characteristic function is the expectation e to the I u z. So u is a real parameter and I is the square root of -1. So this is the characteristic function. And so it is a function of this u. And we typically, as a subscript, put the name of the random variable. Okay. Now, if we have a random vector or a collection of random variables, so random vector, so this will be z now, z1, z2, all the way to zn, then the characteristic function is the expectation of e to the I. Then you have u1, z1 plus I, u2, z2, all the way to I, un, zn, which means that now this is a function that will depend on n, big N real parameters, u1, u2, all the way to un. And so this is the characteristic function of a random vector with big N components, or we can say that it is the joint characteristic function of n random variables z1, z2 to zn. For a Gaussian random variable with a non-zero, with a strictly positive variance, then this is the PDF. What about the characteristic function? The characteristic function, it looks like this. So if our random variable is Gaussian and it has a mean gamma and variance sigma squared, then the characteristic function is e to the I, u, and then the first moment, or the mean, which is gamma, minus 1/2 u squared, sigma squared is the variance. And this is an if and only if statement in the sense that if my random variable is Gaussian, this is the characteristic function. If I am playing with characteristic functions and then I get one that looks like this, then this is indeed the characteristic function of a Gaussian random variable with mean gamma and variance sigma squared. The characteristic function of a random vector with independent components, or we can say the characteristic function of independent random variables, is the product of the characteristic functions. Affine transformation of Gaussian vectors yields a Gaussian vector. So suppose that we have a vector, a Gaussian vector n by 1, which means that the components of this vector are random variables and those guys are jointly Gaussian. So they satisfy this property that a weighted sum of them will give us a scalar Gaussian random variable. Now suppose we take x and we do an affine transformation. We multiply x by a given deterministic matrix A, let's say of size s by n. And then we add a vector b of size s by 1. By doing this, we are making a change and we obtain a new random vector y with basically s random variables. If x is a Gaussian vector, y is a Gaussian vector. if the components of X are jointly Gaussian, the components of Y are jointly Gaussian. How can we prove this? So we need to verify that if I take the components of vector Y and construct a linear combination, a weighted sum, then no matter what weights I choose, the weighted sum will be a Gaussian random variable. This is the idea. I mean, so basically, we will try to verify the definition. Consider beta. So beta is a vector, beta 1, beta 2, all the way to beta s. Every beta here is a real number. Now, what is beta transpose y? Beta transpose y is the inner product. So this is beta 1, beta 2 to beta s. And this is y1, y2 to ys. So if we multiply the row vector by the column vector, we will get beta 1, y1 plus beta 2, y2, and so on. So this is beta transpose y, and the expectation of this quantity here is basically beta transpose the expectation of y. And the expectation of y, okay, so this expectation is beta transpose the expectation of y. And what is the expectation of y? Y is defined in terms of vector x. So this is A times the expectation of vector x. Remember, this was the column vector, eta 1, eta 2, and so on. And then we have B. So the expectation of beta transpose y is beta transpose A eta plus beta transpose B. Now, if we take beta transpose y, subtract the mean, okay, then the variance of beta transpose y is basically, so what is the variance? This variance, it is the second moment of this quantity, beta transpose A, x minus eta squared. Okay, so to find the variance of the quantity, we subtract the first moment. So we basically have minus expected value of beta transpose y, and then we take the expected value of the square. So now we have this thing. Now this is a scalar, and I can write down this scalar as beta transpose A x minus eta, and then I can take its transpose, because a scalar is a 1-by-1 matrix, so it's a transpose itself. Okay, so rather than writing this as a square, I will write this quantity as beta transpose A times x minus eta times it is times itself. Okay, but I will write this second copy as beta transpose A x minus eta all transpose, which again, for a 1-by-1 matrix, the transpose of the matrix is itself. The reason for doing this is that this transpose is x minus eta transpose, then A transpose, then beta. So we read it in this order. So x minus eta transpose, A transpose beta. And so when we apply expectation, we will get, those guys are deterministic. So let's take them outside to the left and to the right. And then we end up with the expectation of x minus eta transpose. This is our matrix from the first slide. This is basically the covariance matrix of random vector x, and it is the matrix whose element kv gives the covariance between xk and xv. Those are, the random variables. Those are two of the random variables living as components of vector x. So this is basically beta transpose A, CXX, our old friend, A transpose beta. So the strategy here is that I will construct a weighted sum of the components of vector y. What is this weighted sum? The weighted sum is beta 1 y1 plus beta 2 y2 all the way to beta n yn. So this is step one. This is a random variable. Number two, I will try to compute the characteristic function of this random variable, which by definition is the expectation of e to the I, which is square root minus 1 u. So the characteristic function is parameterized by the real parameter u, and then this is the random variable under investigation. So what we are trying to do is that we are trying to compute the characteristic function of beta transpose y, and this is nothing but the weighted sum. Now, if we end up with the characteristic function of a Gaussian random variable, regardless of our choice of the betas, then we are done. Then it means that this weighted sum is always a Gaussian random variable, and that's exactly the definition of y being a Gaussian vector, or the components of y, y1, y2 to ys being jointly Gaussian. So this is the game plan. Form a linear combination of the components of y and find the characteristic function. Okay, find the characteristic function and check whether the characteristic function you obtain is some general characteristic function or it is specifically the known characteristic function of a Gaussian random variable. So you start like this, and then you say, well, my problem is that vector y itself is an affine transformation of random vector x. So replace y by ax plus b, and so this is what we have here. So here we just used the fact that vector y is obtained by taking vector x, multiplying it from the left by matrix A of size S by big N, and then adding this vector B of size S by 1. Okay. Now, this exponential can be split into two exponentials, and one of them is non-random because B is a given vector, beta is again is an S-dimensional vector of deterministic quantities. So those play no role when we take expectation. So this part here can be pulled outside the expectation, and then we are left with e to the IU beta transpose AX, okay, which I can write as alpha transpose. Okay, so this thing here, this guy E, I will write it as e to the IU alpha transpose X, where alpha is A transpose beta. Okay, and so alpha transpose is beta transpose A as we have here. So this is the expectation that we have. And now it is an expectation that depends on X. It is given, this is our starting point, that vector X itself is a Gaussian vector. Its components are jointly Gaussian. The components are jointly Gaussian. So what does it mean that the components are jointly Gaussian? It means that alpha transpose X, which is nothing but a weighted sum of the x's, alpha 1, x1, all the way to alpha n, xn, because X is a Gaussian vector, then regardless of our choice of the alphas, this weighted sum is a Gaussian random variable. It's a Gaussian random variable. That's a given. And so this is the characteristic function of the Gaussian random variable alpha tx. Okay, so this is the characteristic function of Gaussian random variable alpha transpose x, which we encountered when we defined what joint Gaussianity means. So again, we will take this result for granted. Whenever I see Gaussian random variable, then there is an established expression for its characteristic function. Well, the characteristic function of a Gaussian, it's basically obtained using contour integration, and it is not that difficult, but again, we will take it here for granted. And the characteristic function is e to the IU, and then we put the first moment of this Gaussian random variable. And the first moment of this Gaussian random variable is alpha transpose eta, where eta is this column vector first component is the first moment of x1, second component is the expected value of x2, and so forth, minus 1/2 u squared, and then we have the variance of this quantity. So remember, the variance of this quantity is the double sum, which can be written as this quadratic form, alpha transpose cxx alpha. So moving from here to there is we are basically exploiting the fact that x is a given Gaussian vector. Okay. Now we know that alpha is given by such, so rewrite things again in terms of beta. Okay, so this is what we don't forget what we are doing. We are trying to obtain the characteristic function of this weighted sum here of the y's. We are trying to verify that the y's are indeed jointly Gaussian. We used the fact that vector x itself is jointly Gaussian and that y is related to x via the affine transformation y is equal to a x plus b. We obtained this characteristic function, but then you look at it and then you say, well, what is this characteristic function? It is something like, it is e to the I u and then something. This thing is beta transpose b plus beta transpose a eta, and this quantity here is exactly the first moment of beta transpose y. Then we have minus 1/2 u squared, and then we have beta transpose a cxx a transpose beta. When we computed the variance of this guy by computing the second moment of this guy, this is what we obtained. Remember this trick when we took the square, wrote it as, you know, a 1-by-1 matrix times its a transpose, and then we applied the expectation and we obtained here the covariance matrix of random vector x. Well, this thing is exactly the value. So again, we have a uniqueness theorem regarding characteristic functions, which means that if you see this characteristic function, then you know indeed that the random variable is Gaussian random variable. Did our result depend on a particular choice of the betas? No. For any collection of the beta values, we will obtain a Gaussian random variable, and this is the first moment, and this beta transpose a cxx a transpose beta will be the variance. So this means that the components of vector y are indeed jointly Gaussian, because any linear combination of them is a Gaussian random variable. And so the vector y which is obtained by an affine transformation of Gaussian vector x, is itself a Gaussian vector. Note that if you have a collection of jointly Gaussian random variables, then each one of them is Gaussian. But the converse is not generally true, which means that, you know, if we know that we have random variables that are Gaussian, perhaps they are not jointly Gaussian, because maybe there is a particular weighted sum of those guys that is not a Gaussian random variable. Okay, so this is very important. However, if we have random variables, each one of them is Gaussian, and they are independent, then in this case, we are sure that those random variables, this collection, or basically if we gather these guys as components of vector x, then vector x will be a Gaussian vector. So if you have Gaussian random variables and that's it, you know, you don't know anything about them other than that each one of them is Gaussian, you know, it's not guaranteed that they are jointly Gaussian. But if we know further that they are independent, then yes, they are jointly Gaussian. How do we verify this? Use the definition. We will take a weighted sum of those x's. Okay, this is a weighted sum, and the strategy is simple. If we can prove that this weighted sum is always a Gaussian random variable, regardless of our choice of the betas, then it must be the case that those x's are jointly Gaussian. So we will form this weighted sum. Let's prepare ourselves by computing the first moment. So the first moment, apply expectation by linearity of expectation. This will be summation k from 1 to big N beta k expected xk, which we called eta k. And then for the variance, now the variance of this summation is not a double sum. Okay, so if you do the variance of y generally, so generally, this will be summation k from 1 to n, summation j from 1 to n, then beta k, beta j, then covariance of xk, xj, as we did on the first page. This is the general case. But if we know that our friends here are independent, then if they are independent, then they are pairwise uncorrelated, which means that if these two indices differ, then the covariance is equal to 0. So the surviving terms are only n terms when these two indices are equal. So k is equal to j is equal to 1, k is equal to j is equal to 2, and so forth. And in that case, covariance xk, xk is simply the variance of xk. So because the x's are independent, this is the variance of y. We can see it in another way, that since we know that those guys are independent, then we can apply the rule that the variance of the sum is the sum of the variances. And so the variance of y, because we have independence here, which implies uncorrelatedness, then the variance of this sum is the sum of variances. This is a constant, so we take it outside the variance as beta k squared, and then we have the variance of xk. So this is the first moment, and this is the variance of y. We do not know yet what y is in terms of distribution. If we can show that it is Gaussian regardless of the betas, then indeed, the x's are jointly Gaussian. So again, the way to go is to make use of the characteristic function. We will obtain the characteristic function of this random variable y, and hopefully we will end up with the characteristic function of a Gaussian random variable. Characteristic function expectation e to the I u big Y, which is given by this summation. Now we can take the exponential and write it as a product. We can do this from the properties of the exponential. Then we can exploit the fact that the x's are independent. So because the x's are independent, the expectation of the product is the product of expectations. So this is going from here to there. Basically, we have exploited the fact that the x's are independent. Now we know that each one, each one of those guys is Gaussian. Okay, so we have an expectation of e to the u beta k xk. Let's remember what is the characteristic function of a Gaussian. If z is Gaussian, gamma and sigma squared, then the characteristic function of z is e to the I u, the first moment, which is gamma, and then minus half u squared and then sigma squared. So now we have the xk is a Gaussian random variable. This looks like the characteristic function. We can basically think of u beta k as u. You know, we can think of this as one unit, as something, just one quantity. Okay, let's call this thing u bar. So this is expectation of e to the u bar xk, right? And we know that xk is Gaussian, it's given. So this will be e to the I u bar, and then the first moment of xk minus 1/2 u bar squared, and then the variance of xk. And then we can write u bar again as u beta k. Okay, so we use the given fact regarding the characteristic function of Gaussian random variables, and this is what we get for this characteristic function. So this is the characteristic function of xk of u beta k evaluated at u beta k. And now we have exponentials that are multiplied, so we can add the exponents. And when we add the exponents, you know, the terms will collect, so that we have here the expected value of y, and we have here the variance of y as computed initially. And this looks exactly like the characteristic function of a Gaussian random variable. So y, which is a weighted sum of the x's, is always a Gaussian random variable, regardless of our choice of the betas. So it means that the x's are jointly Gaussian. So if we have Gaussian random variables, moreover, we know they are independent, then they are jointly Gaussian, and any linear combination of them will yield a random variable that is Gaussian. Now we have jointly Gaussian random variables x1, x2, all the way to xn. And suppose that we know that those random variables are pairwise uncorrelated. So we know that for general random variables, independence implies uncorrelatedness. So if two random variables are independent, it must be the case that they are uncorrelated. So if you compute the covariance is exactly 0. Independence implies uncorrelatedness, 0 covariance. The converse is generally not true. So you can come up with examples in which two random variables are uncorrelated. Their covariance is equal to 0. However, they are dependent, which means, for example, if they are absolutely continuous, their joint PDF cannot be written as the product of PDF of each one of them. But if our random variables are jointly Gaussian, then uncorrelatedness implies independence. So if we have a bunch of jointly Gaussian, they must be jointly Gaussian random variables, then if we show that they are pairwise uncorrelated, then it must be the case that they are independent. This is the characteristic function of those n random variables, and as I said, that basically the characteristic function it is parameterized by n parameters, n real valued parameters, and it is this expectation I u1 x1 plus u2 x2 all the way to un xn. This is the joint characteristic function, or just the characteristic function of the Gaussian vector x here. And now if you look to this characteristic function, u transpose x is a linear combination, a weighted sum of the x's. And because the vector x is Gaussian, its components are jointly Gaussian, then this weighted sum here must be a Gaussian random variable. And this weighted sum here, it has a mean value which is equal to U transpose. So the mean value is U transpose eta. So it's this summation here. So you take each U and multiply by the expected value of the respective x. And the variance is the quadratic form, is this double sum, summation k from 1 to n, summation j from 1 to n. Then you have uk, uj, and then the covariance. So remember, this is the thing that we can write as a quadratic form, u transpose c, x, x, and u. This double sum here can be written as two terms. In the first one, it has big N terms. Those are the terms in which the two indices are equal. So k equal to j equal to 1, k equal to j equal to 2, and so on. And then there are n squared minus n terms in which k and j are basically distinct. They are different because our random variables, they satisfy this property. They are pairwise uncorrelated. So the covariance of xi and xj is equal to 0. If I and j are different, then all those terms will disappear and we get this summation here. Okay. And this can be obtained directly by saying, well, let's take the variance of this sum. The x's are pairwise uncorrelated, so the variance of the sum is sum of variances. And so you take the variance of uk xk, it will give uk squared and the variance of xk. So here we are exploiting the fact that the x's are pairwise uncorrelated. The idea is that for general random variables, being uncorrelated does not necessarily imply that they are independent, but here we will show that actually uncorrelatedness will lead to independence. That's the characteristic function of vector x. By definition, it is expectation e to the I u transpose x. So this thing is u1 x1 all the way to un xn. Rather than thinking of this as the characteristic function of a random vector x, we can take u transpose x as a random variable, and we imagine that this expectation, it is e to the I and then 1. The parameter of the characteristic function is 1, and then we have a scalar random variable which is u transpose x. Okay, so this is the definition of the characteristic function of a random vector, and it can be thought of as if we evaluate the characteristic function of u transpose x. This is our scalar random variable at 1. U transpose x is a Gaussian random variable. Why? Because the x's are jointly Gaussian. So regardless of the values of u1, u2, all the way to un, regardless of what u's we use, then u transpose x is guaranteed to be a scalar random variable. And so the characteristic function of a scalar Gaussian evaluated at 1 is e to the I times 1 times the first moment, or the mean of this guy, which is this one here, minus 1/2, and then this parameter squared, which is 1, times the variance of u transpose x, which is given by this sum. We don't have a double sum anymore because it is given that the random variables x1, x2, and so on, they are pairwise uncorrelated. So this is the characteristic function that we have here. We have sums in the exponent, okay, and so we can write down this as e to the summation k from 1 to n, and then I uk expected xk minus half uk squared variance xk. And then rather than having a sum in the exponent, we can write down this as a product of exponentials. And if you look at each exponential, it is exactly the characteristic function of xk. This is the characteristic function of xk evaluated at uk. So we started with the characteristic function, the joint characteristic function. And then we discovered that it can be written as a product. And this is a proof that the random variables are independent. If you can take the joint characteristic function and you can write it as a product of the characteristic function of each one of those guys, then that's independence. Okay, so this is very nice. Sometimes it is difficult to prove that two random variables are independent. But if we have two random variables and they are jointly Gaussian, then to prove independence, it is enough that we prove that they are uncorrelated. Now, suppose that we want a general formula for the characteristic function of a Gaussian vector, okay? So what we have is that if x is Gaussian with mean value eta and some variance, let's say sigma squared, then we took it for granted, you know, that the characteristic function is e to the iu eta minus half u squared sigma squared, and this is obtained again by taking basically this expectation here. This is expectation. You know, we know the Gaussian distribution minus x minus eta squared over 2 sigma squared. And then we multiply by e to the I ux dx from minus infinity to infinity. So basically that's the expectation written here as the integral of this term here times the Gaussian PDF. So you do the integration, it requires contour integration in the complex plane. And so we end up with this thing. Now, what is the characteristic function of a Gaussian vector? So we are talking about the joint characteristic function of a bunch of jointly Gaussian random variables. So we want this thing. And so the trick now, we did it before that, well, this is the expression for the joint characteristic function of x1 all the way to xn, but we can think of it as the characteristic function of the scalar random variable u transpose x, which is known to be Gaussian. Is known to be Gaussian because x is a Gaussian vector, and u transpose x is a weighted sum of the x's, and by definition this will be a scalar Gaussian random variable. So it is phi of u transpose x evaluated at 1. And so basically we can use the formula for the scalar random variable if we replace this eta by the mean or the first moment of u transpose x, and we replace sigma squared by the variance of u transpose x, and that's it, and we are done. So the joint characteristic function of a Gaussian vector is simply the Gaussian characteristic function for a single or just one random variable. And we do this trick that the characteristic function of the vector is the characteristic function of u transpose x evaluated at 1. Now, if x is a general vector, then who knows what this thing is, what u transpose x is? But by definition, If X is a Gaussian vector, if its components are jointly Gaussian, then we are sure that U transpose X is a Gaussian random variable, regardless of what U1, U2, all the way to UN are. Okay, so this is basically the trick that will allow us to write down the joint characteristic function. We just need to replace eta by U transpose eta, right? Because the first moment of U transpose X is U transpose eta, and we need to replace sigma squared by the variance of U transpose X, and the variance of U transpose X is this thing. If we write it in as a double sum, right? So Ui, Uj, and then, you know, the covariance of Xi, Xj, or as a quadratic form, it will be U transpose Cxx U. That's it. Okay. And here we go. And so this is the expression for the characteristic function of a Gaussian vector, a vector whose components are jointly Gaussian random variables. Note that in writing the characteristic function, it is not a must that Cxx is positive definite. So we know that the covariance matrix of a random vector is, generally speaking, it is positive semi-definite. So it is symmetric, and its eigenvalues are real valued. Moreover, it is positive semi-definite, so the eigenvalues are non-negative. There is no, because here we use Cxx directly, not its inverse or anything. Okay, so this is one advantage for using the joint characteristic function of a Gaussian vector. We do not need to worry whether Cxx is invertible or not. If it has a zero eigenvalue, 1 eigenvalue or more, it's okay. It's not a problem. But to write down the PDF, we will need to assume that Cxx is invertible. And because it is a symmetric matrix, we can make use of its eigendecomposition, that Cxx can be written as a unitary Q matrix. The columns of this Q matrix are eigenvectors, and then we can have a diagonal matrix containing the eigenvalues, which are generally non-negative. And if our matrix Cxx is invertible, then the eigenvalues living on the main diagonal here, they will be strictly positive. And then we have the inverse of this matrix Q, and since it is unitary or orthogonal, we can say orthogonal, then the inverse is Q transpose. We took it for granted that if X is Gaussian, that we know its PDF, its probability density function, that it looks like this. X minus, then we subtract the mean square over 2 sigma square. The question is, now suppose that we have run a Gaussian vector, or we have a bunch of jointly Gaussian random variables, x1, x2, all the way to xn. What is the joint PDF? So in other words, our goal is to derive the multivariate Gaussian distribution. And for this one, we will need to assume that the covariance matrix is invertible. So it is positive definite. Its determinant is strictly positive. All the eigenvalues are strictly positive. Okay. How can we use what we know about the PDF of a scalar Gaussian random variable to obtain the PDF of a Gaussian vector, a collection of Gaussian random variables that are jointly Gaussian? So the trick here is to use the fact that if we have n Gaussian random variables that are independent. If they are independent and each one of them is Gaussian, then they are jointly Gaussian. And because they are independent, then their joint PDF is very easy. The joint PDF is just the product of the PDF of each guy. So if this question regarding what is the multivariate Gaussian distribution, if the components of our random vector are independent, or we prove that if they are pairwise uncorrelated, then they are independent, then it is easy to write down the joint distribution. But the question now is, what is the multivariate Gaussian distribution in the general case, where we have a general covariance matrix only with this basically requirement that the matrix is invertible, is non-singular. So we will start with a vector y, y1 to yn is a vector, and we will assume that those vectors are IID standard Gaussians. Okay, so those guys are have a mean of 0, variance of 1. They are independent, and so basically y is a Gaussian vector. The y's are jointly Gaussian. Now take x. So this is the trick. Take x to be a particular affine transformation of vector y. So y is an easy vector, and y is a vector, again, for which you can very easily write down the joint PDF of those components, exploiting independence. So the joint PDF will be the product of the marginals. Now write down x in this particular way. So x is an affine transformation of y. So we will take y, that's a column vector with n components. We multiply y from the left by a matrix, an m by n matrix. It is basically the square root matrix cxx to the 1/2. And of course, what is this thing? What is the square root of a matrix? So because the matrix is symmetric and positive semi-definite, then we can write it down as, as we did on the previous slide. It is a matrix of eigenvectors and it is orthogonal. Then we have a diagonal matrix. Okay, so this contains the eigenvalues, and those guys are, for a general covariance matrix, those guys are non-negative. If we assume the covariance matrix is invertible, then those guys are strictly positive. And then here we put the inverse of the orthogonal matrix, that's the transpose. So what is this thing here? For symmetric positive definite or symmetric positive semi-definite matrices, this thing is defined as, so we define it as the matrix that is obtained from the eigendecomposition of cxx by taking matrix Q, then Q transpose, and then in between we put a matrix in which we have the square roots of the eigenvalues. And this is the positive square roots. And this is an unambiguous computation, right? Because, those guys are real valued and they are non-negative in the general case, positive in our case here. And so, the square root, the positive square root of a positive number is unique. So this will be cxx 1/2. And it is called the square root of the matrix because if we take this guy and multiply it by itself, what we get is Q and then the matrix with the square roots, Q transpose, and then another Q, and then the matrix of the square roots, and then Q transpose. Q is an orthogonal matrix, so this gives identity. And then we multiply these two diagonal matrices, they will give us big lambda. And so this is equal to Cxx. So that's the reason, sometimes this is called the square root of the matrix, because it is the matrix that if we square, if we multiply by itself, we will get Cxx. And then we add vector eta here. Now, eta is the vector of the first moments of x. Okay. Now, if we define x in this way, x is an affine transformation of the Gaussian vector y. Why y is a Gaussian vector? It is a Gaussian vector because each y is Gaussian and they are independent. So the components of vector y are jointly Gaussian. Then our first theorem was that an affine transformation of a Gaussian vector gives a Gaussian vector. So x is indeed a Gaussian vector because it's an affine transformation of vector y. So what are the statistics of x? If you take the expected value of x, it is this matrix times the expected value of vector y plus eta. Eta is a constant, and so its expected value is itself. And the y's are zero mean, and so this will disappear, and this eta is the mean vector. So basically, it's the vector that contains the first moments of random variables x1, x2 to xn. And what is the covariance matrix of x? Let's see the covariance matrix of x. So we will take x minus eta times x minus eta transpose. We apply the expectation. So this will be x minus eta is this matrix times y. Then transpose this. If we transpose, we get y transpose. And Cxx to the power 1 over 2, it's a matrix. If you take its a transpose, Q transpose transpose is Q. A diagonal matrix transpose is itself Q transpose. You will get the exact same matrix. So Cxx to the 1/2 is also a symmetric matrix. We do not need to write the transpose. And then those guys are given. They are deterministic matrices. Expectation y transpose is the covariance matrix of vector y. Vector y is composed of NIID, standard Gaussian random variables. So the covariance matrix is identity. And then we have these two matrices multiplied together, which will give us Cxx. By defining x to be this matrix y times y plus eta, so vector x is a Gaussian vector. Its components are jointly Gaussian random variables. The means are in vector eta, and the covariance of x is Cxx. And what we put here to construct vector x is the square root of matrix Cxx, designed as explained. We do the eigen decomposition of Cxx, and then we take Q, the matrix of the orthogonal matrix of eigenvectors. We take Q transpose, but then we replace the diagonal matrix of eigenvalues by a diagonal matrix in which we put the positive square roots of those positive eigenvalues. Now we need to go from the PDF of y, vector y, the joint PDF of the random variables living in vector y to x. We need to do a transformation or a change of variables. The PDF of y, because the components are independent, so that's a product. Okay, so we have a product here, and each one is a standard Gaussian. So this y here, so this is a vector that contains y1, y2, all the way to yn over 2. And this is 1 over 2 pi to the power n over 2. And then we have e, and then we have the sum of the squares here, yk squared over 2. That's the PDF of y, straightforward because of the independence assumption. So we can just multiply the marginal PDFs. But then we need to apply this formula to go from y, from the distribution of vector y to vector x. And so the rule is that we will take this distribution here and we will replace the y's by the x. So we need to do this. So we need to express y in terms of x. X is x to the half and then y plus eta. So move eta to the other side. And now you can see why we need that the matrix is invertible. So we'll multiply by basically the inverse of this matrix. And this matrix is invertible, right? Cxx to the 1 over 2, it is a matrix. This is its eigendecomposition. So the eigenvalues are strictly positive, and the determinant is strictly positive. It is an invertible matrix. And its inverse will be Q, and then Q transpose here, a diagonal matrix, and we will have those guys. And you can check that if we multiply this and that, we get identity. If we do the multiplication, then there will be Q transpose Q that is identity. And then when we multiply this matrix by that matrix, we get another identity. And then we will get again something like QQ transpose, which is identity. So this is indeed the inverse. And to have it, we will need all eigenvalues to be strictly positive. Y is Cxx minus 1 over 2, x minus eta. So this is how we go from y to x. Note here that what we have is in the expression for the joint PDF of the components of vector y, we have here the L2 norm squared of the vector. This is the sum of the squares. It's the L2 norm square, which can be written as y transpose y, right? Because this thing y1, y2 all the way to yn, and this thing y1 all the way to yn. So when we multiply the row vector by the column vector, we get y1 squared plus y2 squared, and so on. So the sum of the squares is the L2 norm squared, or it is y transpose y. And so if we do the change so that now we have an expression in terms of our x random variables, then this guy here will be, this term here will be replaced by y transpose. So this will be x minus eta transpose. And then this is a symmetric matrix. So its transpose is itself. And then y. And so y will give us this expression here. And these two guys can be combined as x minus eta transpose Cxx minus 1 x minus eta. This means that rather than having the L2 norm squared of y, we will have this expression here in the multivariate Gaussian distribution. And as you can see, this is parameterized by the mean vector, this column vector that contains the first moments or the means of x1, x2, all the way to xn. And it has also the inverse of the covariance matrix. And that's the reason that we, in the characteristic function, if you remember from the previous slide, the multivariate characteristic function makes use of Cxx without inverse or anything. So there is no problem if Cxx, is, singular. But here to write down the PDF of the multivariate Gaussian vector, then we need this matrix to be invertible. Are we done? No, because the change, to go from the joint PDF of the y's to the joint PDF of the x's, it is not just that we go to this PDF and do this replacement. we will need also to divide here by the Jacobian of the x's with respect to the y's. So this is the absolute determinant of the Jacobian matrix. And the Jacobian matrix here is straightforward because, you know, the components of vector eta are like constants. If you take the partial derivative, of one of the x variables with respect to one of the y variables, what will be the derivative? The derivative will be an element in this matrix that is linking the two guys. In fact, the Jacobian matrix of the transformation is just this matrix itself. I mean, you can write down this thing using the components and then take the partial derivatives. You will discover it's a linear, you know, this thing here is a linear transformation. The Jacobian matrix is this quantity, and we need to take its absolute determinant. And what is the determinant? What is the determinant of our friend here? What are the eigenvalues? So the eigenvalues are those guys. And so the determinant that we have here is square root lambda 1, square root lambda 2, all the way to square root lambda n. And so it is the square root of the product of the lambdas. And the product of the lambdas, you know, those are the eigenvalues of Cxx itself. So in the denominator here, we have the square root of the determinant of the covariance matrix Cxx. Okay. And so this is the distribution of the y. This is easy. This was basically the main game here. The main game is start with something you can write down its PDF very easily. So just a Gaussian vector with standard Gaussian IID random variables, and then say that x, you want to write down the distribution for a general Gaussian vector x, construct x from y by doing this affine transformation, multiply y by this matrix, and then add the vector. You know, so this matrix, if you square it, this should be the covariance matrix of random vector x, and this eta is the mean vector. Now, if we replace the y's, you know, if we express y in terms of x and do the substitution, and you know, and then we should take into account the Jacobian of the transformation, we end up with the well-known multivariate Gaussian distribution. And as you can see, the distribution is parameterized by the mean vector eta and by the covariance matrix Cxx. This is the special case, which is the bivariate case. If we have just two random variables, x1 and x2, and in this case, the covariance matrix will be a 2 by 2 matrix. The main diagonal elements, and this is general, will be the variances, and the off diagonal elements here, because we just have two random variables, so it will be the covariance of x1 and x2. And typically we write down the covariance in terms of the correlation coefficient. So the covariance is equal to the correlation coefficient multiplied by the variance of x1, a square root of the variance of x1, so the standard deviation of x1, multiplied by the square root of the variance of x2. Okay, and so we can write down the expression using basically the means and the variances, and rho. Rho will be the correlation coefficient. Okay, and so going from here to there, the covariance is rho times the standard deviation of x1 times the standard deviation of x2, which is sigma 2. Then the determinant of this expression here will be sigma 1 squared, sigma 2 squared, minus, we multiply these guys, so rho squared, sigma 1 squared, sigma 2 squared. So it's 1 minus rho squared, sigma 1 squared, sigma 2 squared. This is the determinant. And we can obtain the inverse matrix. Just divide by the determinant, and then we swap these two guys, and we invert the signs of the off-diagonal elements. So this is the determinant, and this is the inverse of CXX. And in the numerator, remember the general rule is that in the the exponent is -1/2, and then we have x minus eta transpose CXX inverse x minus eta. And so we have this quadratic form. We can write it down because we have an explicit formula for the inverse, and then we can do the multiplication, and we will end up with this bivariate Gaussian distribution. In some applications, we are interested in the conditional distributions and the conditional statistics. So here we have big N plus big K jointly Gaussian random variables, x1 to xn and y1 to yk. They are jointly Gaussian. So now we understand the game. So it means that if we construct a linear combination, a weighted sum of those guys, no matter what the weights are, then the resulting scalar random variable will be Gaussian. So that's that's how we show that random variables are jointly Gaussian. And if we just know that each one of them is Gaussian, and moreover we know that they are independent, then this is a guarantee that they are jointly Gaussian. Let's take the x's and use them to build an n by 1 column vector x. So this will be random vector x. And let's do the same to the y's. So we have those random variables y1 to yk in random vector y. And we are interested in x, the statistics of x given y. X given y. Okay. Now, this is, for example, if we have, if the y's are observations, and we want to estimate the x's, then, for example, the expectation of x given y, this vector is the so-called minimum mean squared error estimate. So those quantities here are used like in estimation when we have jointly Gaussian random variables and we want to do minimum mean squared error estimation. What is this expectation? It is a conditional expectation. So vector x itself, it has a vector of means or first moments, expectation of x1, x2, all the way to xn. But now we have a vector, which is this vector here, in which each expectation is conditional. It's conditioned on the y's. So it's as if we know the y's. So the practical application again is that like the y's will be like measurements, observations, data that are collected. So the y's will be known. And we ask ourselves, can we have an estimate for the x's? And sometimes, again, in minimum mean squared error estimation, where our variables or our unknowns and the observations are jointly Gaussian, the solution, that minimizes the mean square error is expectation of x given y. So it is a vector of the expected values of x1 and x2 all the way to xn, but those are conditioned on all the y's from y1 to yk. So conditioned on the random vector y. Now, the conditional covariance matrix is defined in a similar way. So what is the covariance matrix itself? You take the expectation, take x, you subtract the mean vector, and then x minus the mean vector, and then transpose. So we have the outer product of this vector with itself, and this is the covariance matrix. Now, the conditional covariance matrix, when you subtract the conditional expectation, which requires knowing the conditional distribution of vector x given vector y. So we subtract this, and then we basically take the vector times its transpose, and when we compute the expectation, this expectation here, again, we do it given y, conditioned on y1, y2 to yk. Cxx is the covariance matrix of vector x. This is unconditional. Cyy is the covariance matrix of vector y. Cxy is the so-called cross covariance matrix. And so here we have the expectation of x minus expected x, y times expected y transpose. So this matrix contains elements. They are basically the covariance between one of the x's and one of the y's. So the covariance matrix, sometimes it's called the auto covariance, because here the elements of Cxx, we measure the covariance between one component in vector x and another component in the same vector. Here we are computing the covariances between the random variables in x and the random variables in y. And the Cyx is basically Cxy transpose. We will assume that Cxx and Cyy, those two covariance matrices, are inverted. So here is the claim. What are these two quantities? The claim is that this conditional expectation given y is Cxy, which is this matrix, the inverse of Cyy, and then we multiply this by y minus the expected value of y. And to this term here, we add the mean value of x. That's the unconditional mean. And for the conditional covariance matrix, it is Cxx minus Cxy, Cyy inverse Cyx. First order of business is write down the joint distribution of the x's and y's. So this is basically the multivariate Gaussian distribution of big N plus big K random variables. Those guys are jointly Gaussian. So the expression of the multivariate Gaussian distribution, we will have 1 over 2 pi, and then over 2, and here we put the number of variables we are interested in. Here we have n plus k, x1 to xn, and then y1 to yk. Then here we will put the determinant of the covariance matrix of the vector x1, x2 to xn, y1 to yk. So this is the C is the covariance matrix of the whole collection of n plus k jointly Gaussian random variables. In other words, that the C matrix here is the expectation of this vector minus its mean value. So rather than writing x minus the mean and y minus the mean, I will just write x bar, y bar. So here they are stacked together. This is n by 1, and this is k by 1. And then we multiply this by the row vector, the row version, x bar transpose, y bar transpose. So the bar is just, so rather than write x, this is x minus its mean vector. This is y minus its mean vector. So the expression for the multivariate Gaussian distribution must contain the covariance matrix of all the guys, all the n plus k random variables. And so to compute it, we need to stack vector x over vector y, for example, like this, to have an n plus k random vector with n plus k jointly Gaussian random variables. And then we find the outer product. Of course, from each of the x's and y's, we need to subtract the mean. And this will be C that is used in the expression here. So it is an inverse in the exponent, and then we need to compute its determinant in the denominator. So if we do the multiplication blockwise, then we are computing the expectation here. We have x bar transpose, x bar y bar transpose, y bar x bar transpose, y bar transpose. If we apply expectation, which means that we apply it element wise, then our matrix C, this block here, this n by n block, will be expectation of x bar transpose. Don't forget that x bar is x minus the mean vector. So this will be CXX. This will be the covariance matrix whose elements are the covariances between one element in vector x and another element in that vector x. And it, on the main diagonal, we will have the covariance between, an element and itself, which is the variance. And here we will have CYY, that's a K by K. And then here we will have the cross covariance matrices we defined on the previous slide. So this is CXY and this is CYX. So the covariance matrix is n plus k, and it's divided into those 4 blocks here: CXX, CYY, CXY, and CYX is the transpose of CXY. This is the multivariate distribution applied to all the jointly Gaussian random variables. Now, what is an expression for the inverse? We want to express the inverse in terms of the matrices CXX, CYY, and CXY. It turns out that there is a tool to do this. So if you have a matrix that is divided into blocks like this, then you can show that the inverse of this matrix can be expressed like this. So now we can express the inverse in terms of those blocks that constitute the matrix C. And then we will call this one A, B, B transpose, and D here. Then what do we have in the exponent? So we have the minus half. Here is the minus half. And then what we can do is that we can take x bar, y bar, so transpose, so we convert it into a row vector. And then we have C inverse now. It's A, B, B transpose, and D. So those blocks. And then we have x bar, y bar. So we can do this. We can do this matrix multiplication, right? So this times this will give us AX bar plus BY bar, right? And then we have B transpose X bar plus DY bar. And then we multiply, we take this and multiply it here. So we will get, so I'm sorry, I should put a transpose. So here will be X bar transpose AX bar. So X bar will be multiplied by this guy plus X bar transpose BY bar. And then this Y bar transpose will be multiplied by this element. So Y bar transpose B transpose X bar plus Y bar transpose DY bar. So we do the matrix multiplication using the blocks. Okay, and this is valid in matrix theory, so long as the sizes are okay. And you can check that everything here in terms of the sizes are the sizes match, and these products are all valid. So this is basically the joint PDF of x1, x2 to xn, y1 to yk, and it is expressed. Now we have it written in terms of the matrices A and B and D, and those depend on cxx, cyy, and cxy. Now we will do something. Why are we interested in the joint? Well, our goal is the conditional distribution. We want to do things x given y. What is the distribution of x given y? This is like the main objective here, the goal. But the conditional distribution, by definition, is the joint divided by the distribution of the y vector. Well, the distribution of the y vector, that's a multivariate distribution with, it's the distribution of those jointly Gaussian random variables y1 to ybk, like this. And so it will be parameterized by the matrix C yy, and here in the exponent we'll have cyy inverse, and this y bar is y minus its mean vector. So the denominator here is not problematic. The numerator is the joint distribution, and so the previous steps are to basically manipulate this joint distribution and write it in a way that will help us simplify the final result and get a nice expression for the conditional distribution of vector x given vector y. So let's see what we will do here. This term is isolated. So isolate this term. Now we have three remaining terms. And what we will do is we will write this down as this quadratic form. So x bar minus alpha all transpose A x bar minus alpha. Let's expand this. So this is x bar transpose minus alpha transpose, and then A times this bracket is ax bar minus A alpha. And so if we multiply the brackets, we get x bar transpose ax bar. Note that this guy is this one. And then we have minus x bar transpose A alpha. And then we have minus alpha transpose ax bar when we multiply these two. And then we have plus alpha transpose A alpha. Alpha transpose A alpha. Alpha transpose A alpha is not here, okay? And so we have an extra term. If we account for this minus 1/2 that is outside, then we have an extra term minus 1/2 alpha transpose A alpha. And so we add this term because it was not there. It was not there. What about these two terms? So these two terms will play the role of these two guys. So let's repeat. Y bar transpose dy bar is separated into this exponential. Then we try to write down things as a quadratic form involving x bar minus a vector, and this vector will see exactly what it should be. So I will write this as minus half x bar minus alpha all transpose ax bar minus alpha. If you expand this, you will get four terms. This term is this term. There will be a term here that is new, and it is multiplied by minus 1/2. Because it was not there, we need to compensate and add 1/2 alpha transpose A alpha. Then we have two terms, and these two terms must match what we have, here. Okay, and so see, we want minus x bar transpose A alpha to be like x bar transpose B y bar. Right, so we want this to be like that. Okay, so let's take here in this space between this row vector and this matrix, insert A and A inverse. This is A, and it is represented here by an inverse. This is true if those matrices are invertible. So here we are assuming that CXX is indeed invertible, and the same for CYY. And so this will lead to basically whenever you see an inverse here, then it exists. So to do the comparison, I will insert A inverse. So this becomes X bar transpose A inverse B Y bar. And so to get a match, what should alpha be? This alpha, to generate what we have here, this alpha minus alpha must be A inverse B Y bar. Minus alpha must be A inverse B Y bar. So keep this in mind. If this is the alpha that is chosen here, then again we have an equality. It is just another way of writing down the joint BDF of vectors x and y. Now, this extra term here, let's also isolate it, okay? So no, and let's actually write down alpha using its expression. So what is 1/2 alpha transpose? So there is a minus in the alpha, but we have alpha transpose and alpha. So the minus sign will go away and we'll have 1/2, and then the transpose of this thing will be y bar transpose, and then we have B transpose, and then we have A inverse transpose. Let's see, A inverse transpose is itself. This is A. A inverse is CXX minus CXY, CYY inverse CYX. If you take the transpose, CXX transpose, the covariance matrix is symmetric, so this is itself, minus. Then you take the transpose of CYX and put it here. Well, CYX is the transpose of CXY. So the transpose of this guy is CXY. This is a symmetric matrix, and the transpose of CXY is CYX. So A is a symmetric matrix, and so its inverse is also symmetric, and we do not need like to put AT. So this is alpha transpose. Then we have A, so that's the A. And then we have alpha, so copy. Now you can see that here, these two guys, for example, will give identity, and we are left with 1/2 y bar transpose B transpose A inverse, and then these two guys will give identity, and then BY bar. So this term is also isolated. And we have this expression here. So to recap, we wrote down the joint distribution of the jointly Gaussian random variables x1 to xn, y1 to yk. So that's the distribution of big N plus big K jointly Gaussian random variables. And so this PDF requires the covariance matrix of this augmented vector in which we stack x over y. It's an N plus K vector containing all the random variables of interest. And the covariance matrix is the expectation of the outer product of the vectors here, and those include, that they must basically you compute this expectation after subtracting the mean vectors. Now, we wrote down C in terms of these 4 blocks, and we wrote down its inverse, which is needed here in the exponent, also in a block form. We simplified this quadratic form. We wrote x bar transpose, y bar transpose times this matrix here, times the column vector with n plus k variables. So we extended this, and then we isolated this term. We wrote down this the other terms as x bar minus alpha transpose A, x bar minus alpha, where alpha is chosen so that this form here will cover this term, and that term. So we discovered that alpha must be minus A inverse by bar. When we multiply, we will get a 4th term that is not here. That's this term. And so we will also isolate it after rewriting alpha in terms of A and B and y bar. Now to the conditional distribution. So it is the joint over the PDF of Gaussian vector y. Let's think about these 2 exponentials. If we combine them, we will have exponential and then minus 1 over 2 y bar transpose on the left, y bar on the right, and in between we get the matrix, which is D, and then minus, and then here we have B transpose A inverse B. The question is, can we simplify this expression, D minus B transpose A inverse B? So first, we take those A, B, C, or here A, B, and D, and express them in terms of the original matrices CXX, CXY, and CYY. And so we take so A is equal to this, B is equal to this, and D is equal to this. So we take them and insert them here. And it looks like a very complicated expression. What we will do is that we will take this first part, which is CYY plus CYX minus CXX inverse CXY, all inverse. We will apply the matrix inversion lemma to this expression here. So by the matrix inversion lemma, the output is, we have CYY inverse minus CYY inverse, CYY inverse. And then we have this guy here, this guy there, CYX, CXY. And then we have an inverse. And in this inverse, we will have CYY inverse again. And then these 2 guys will switch. This will come here, CXY, and this will come here, CYX. And then finally, we have the inverse of this guy here. Now take a minus sign from this bracket. And so this is equal to CYY inverse plus CYY inverse, CYX, now CXX minus CXY, CYY inverse, CYX, or inverse, CXY, CYY inverse. So it seems more complicated than the original expression. However, this is the good news. This is exactly equal to that. So these 2 monsters will devour each other, and so this one again is like this one is like this one. These 2 monsters will disappear, and the only surviving term is this one here, the inverse of CY. Okay, that's very good. it means that this expression can really be simplified. But actually, there are even better news. If this is equal to Cyy inverse, then the exponential in the denominator has exactly the same exponent, minus 1/2 y bar transpose Cyy inverse y bar. So these guys will all go away. And now our final expression is this expression here. Don't forget that we already know alpha. Alpha is minus A inverse and then B and then Y bar here. Okay, so Y bar is basically vector Y minus its mean vector. Those are done. Now we need to handle the determinants. Let's focus on the determinant of C. Remember, C is the covariance matrix of the stacked vector in which we put vector X and then vector Y together and compute their covariance matrix. So we want the determinant of C. And here we have an expression for C inverse. So determinant of C is 1 over the determinant of C inverse. That's the relationship between these two guys. And the determinant of C inverse, if it's written using this type of partitioning, then it is the determinant of A times the determinant of the Schur's complement of A. And so this will be D minus B transpose. Then we have the inverse of A, and then we have B. So there is an expression for matrices that are partitioned as such, and basically we take the determinant of A times the determinant D minus B transpose A inverse B. So this will be the determinant of C inverse, and its reciprocal is the determinant of C. But this guy here, D minus B transpose A inverse B, is the same quantity to which we have applied, the matrix inversion lemma, or specifically to this particular part. And we discovered that we will get two guys. One will go with this, and this is just the inverse of the covariance matrix of random vector Y. And so this is Cyy inverse. And determinant of A is basically the determinant of this matrix here, and the it is 1 over the determinant of this matrix. Okay, so for the determinants again, we will take the determinant of C. We can write it down in terms of the determinant of inverse of C, and then we basically obtain the determinant of C inverse using the blocks A, B, and D, and then this is Cyy inverse. And remember that we have also a determinant Cyy here, and those guys will go away, and we are left with the determinant of A. So we now have our conditional distribution, the conditional distribution of vector X given vector Y, where the random variables residing in vectors X and Y are jointly Gaussian. We are conditioning on Y again to model a situation in which the components of vector Y will be observations, measurements. We know them, and based on them, we want to estimate the unknown random variables in vector X. And so we will go for what is the distribution of X given Y. So it turns out that the distribution is a multivariate Gaussian distribution. So here we have 1 over 2 pi to the n over 2. N is the dimensionality of vector X. And here we have the determinant of A inverse. And A inverse is this matrix, Cxx minus Cxy, Cyy inverse Cyx. And then here in the exponent, we have X bar plus this quantity. Okay, so let's write down this thing. So this is x minus the expected value of x plus A inverse by bar. And so I can write this as x minus, open bracket, expected value of x minus A inverse b, and then y bar is y minus the expected value of y. So here we have x minus some vector, and here we have A inverse inverse. You can think of this A as A inverse inverse. This is exactly a multivariate Gaussian distribution. And what is the covariance matrix? To be exact, what is the covariance matrix given y? It's a conditional covariance matrix. Now, the conditional covariance matrix is what we have here. So it is A inverse. It is A inverse because in the formula for the multivariate Gaussian distribution here, we should have the inverse of the covariance matrix. Here we have A. So the covariance matrix, or the conditional covariance matrix given y, is basically A inverse. And from the very beginning, we know that A inverse is CXX minus CXY, CYY inverse CYX, which is this. So this thing is the covariance of x given y. Don't forget that this is an expectation of the outer product of a vector. And what is the vector? And we do this expectation given y, and the vector is x minus, not just the expected value of x, but the expected value of x given y. So what is this conditional expectation? The conditional expectation of x given y is this term here, right? It is, we have x minus, the general form for a multivariate distribution is x minus the mean vector. So this is exactly the mean vector. Okay, and what is the mean vector? So it is expected plus, then or here we have a minus, so minus, and then we have A inverse. So this is A inverse, like this. And then we have B. So we need to go here and B. So B is minus this inverse. So there is a minus. So this minus will make this plus. And the expression of B starts by something that is exactly like this bracket, but inverse, which is nice because these two guys, their product will be identity. And then we have CXY, CYY inverse. CXY, CYY inverse. And then we have Y minus the expected value of Y. So this means that the conditional expectation of X given Y is, these two guys give identity. So it is the cross covariance matrix, CXY, then the inverse of the covariance matrix of vector Y. That's the vector of, that's the covariance matrix of the vector of observations or measurements. These are the random variables we are conditioning on, and then Y, expected Y. And then we have expected, we should not forget this guy, expected X. So that's basically the final result, that if we have a bunch of n plus k jointly Gaussian random variables, we can find the conditional distribution of the n random variables x1 to xn given the k random variables y1 to yk. It turns out that the conditional distribution is also multivariate Gaussian, and it is characterized by this conditional covariance matrix and with this this conditional mean. And basically the expected value of x given y, this is the minimum mean squared error estimator of x given y. And don't forget that this is the case in which x and y, every random variable in x and y, all those guys, they are a happy family. They are jointly Gaussian.